Hello students, welcome to the fifth lecture of this VLSI design course. In the last class we have already studied about the MOS structure. We have tried to analyze the structure of the MOS, the internal band diagram, the energy band diagram of MOS system, the band bending concept, and all these things. In today's lecture we will try to analyze the electrical property of MOS structure. Only the MOS structure, not the MOSFET. Please understand the difference between MOS structure and MOSFET. Until now, we have not studied the effect of voltage or the internal band diagram of complete MOSFET. That is the structure consisting of drain and source. We have just studied the internal band diagram, the energy band diagram of only MOS structure, which consists of a gate, a metal gate, silicon oxide, and a silicon substrate. Fine. So in today's class also we will only study the the effect of external voltage which we applied on the gate, the effect of external voltage on the MOS system. So let's start. So this was actually the mashup of my last class. So we have started with the metal oxide semiconductor structure, then we talked about mass action law, fine, and then we talked about the electron density and hole density in it. Then an important concept, one of the important concepts is Fermi level. You should understand what is Fermi level and the Fermi potential. Fine. So if you want, I'll just repeat once again. The Fermi potential is the difference between the intrinsic Fermi level. It's already drawn here, if you can see. It is the difference between Fermi potential. The Fermi potential is the difference between this level. What is this level? The intrinsic Fermi level and the actual Fermi level of the semiconductor. Fine. So that is the Fermi potential. That is very important. It will be useful when you will be analyzing the MOSFET structure. Fine. And then we also talked about the electron affinity. That is an important concept. Electron affinity, the amount of energy required to move the charge carrier away from the silicon. So this is known as electron affinities, denoted by Qi. One more thing which I believe we have forgotten to study in the last class. We have forgotten to study one important concept. You should remember the Fermi potential, you should remember the electron affinity, and you should also remember one more thing, one more terminology, that is work function. Fine. So the work function of silicon is, let me tell you what is the definition of work function. So work function of silicon is, just a second, let me erase all these things. Yeah, so the work function of silicon. Fine. So the work function, we write it as work function, we call it as work function. Fine. Now the work function of silicon is defined as, we write as phi s. Please understand the difference between phi s and phi f. Phi f denotes the Fermi potential, while phi s denotes the work function. So let me tell you what is work function. Work function of silicon. Work function of the silicon is the total amount of energy, or we can also call it as the voltage, the total amount of voltage or total amount of energy. Fine, one and the same thing here, because we are not considering time. That's why the energy and voltage is one and the same thing here. Fine. You'll get to know all these things as we move on in the syllabus. So the amount of energy required to move the charge carrier out of the silicon from the Fermi level. Remember, from the Fermi level, because Fermi level is what? Fermi level, as we have already studied in last class, Fermi level is the energy level where there is the highest, it is the it is highest probability that the charge carrier would be present there. Fine, that is Fermi level. And since the charge carriers are present here, so instead of studying this, that the charge carrier would be moving from conduction band to free space, rather than this we'll study the amount of energy required to move the charge carrier from the Fermi level, and that is known as work function of silicon. I am again repeating, what is the work function of silicon? Work function of silicon is the amount of energy, just a second, yeah, the work function of silicon is nothing but the amount of energy required to move a charge carrier out to free space from what? From where? From Fermi level. Please remember this. This is one of the important things which you need to remember. This is known as work function. And similarly, there is a work function of metal also, because some energy is required, needs to be given to the metal so that it could conduct. So that would be known as work function of metal. Right? So remember these this thing. This is work function. So we have studied the Fermi potential, we have studied the electron affinity, we have studied the work function, we have studied we also studied that how to calculate the Fermi potential using the energy levels. So this is the formula for calculating the Fermi potential. And then we went towards the composite structure of this metal oxide semiconductor. Fine. And we have studied that when we combine all the three materials, the metal oxide and the semiconductor, then due to alignment of the Fermi level, we have studied this in very detail in the last class, that due to the alignment of the Fermi level, the band will bend towards downwards. The band will bend downwards. Let's see. Yeah, we have studied very clearly that the band will bend downwards. Look at here, look at this. So the band will, look at this also, yeah, this one, the band will bend downwards. Fine, the band will bend downwards. And as you can see, this is what, please tell me, this is Fermi potential. Fine, this is Fermi potential. And look at the difference between Fermi potential in the silicon and at the surface. This is very, very important when you will analyze the operation of CMOS. Fine, this concept would be very, very important. As you can see, the difference, the Fermi potential at the surface is very low as compared to the Fermi potential in the bulk silicon. Fine, this is known as bulk silicon. So there is a difference between Fermi potential. And why this difference has occurred? This difference has occurred due to alignment of the Fermi level of metal and the Fermi level of silicon. Fine, and this concept is known as band bending. Now let's move forward. And again, some voltage needs to be applied to remove this band bending. Similarly, as you already studied in your PN junction diode, that some voltage needs to be applied to remove the depletion layer between PN junction. Fine, to remove the depletion layer, that is known as threshold voltage of diode. Fine. And similarly, for MOS structure also, there is an amount of voltage which you can apply between these two terminals. There is a voltage which you can apply between these two terminals. There is a voltage which you can apply between these two terminals. And what will happen then? Because of applying voltage between these two terminals, the potential difference which was created between this terminal and this terminal will go off. And because of this potential difference, the band was bended. So if the potential difference will go away, then the band will become flat. Instead of curved band, bended downwards, it will become flat, and that particular voltage which you have applied here, which will cause these bands to become flat, is known as flat band voltage, flat band voltage or flat band potential. We also call it as flat band potential. Fine. So you need to remember these 3 to 4 terminologies. Fine. Out of which work function, Fermi potential, flat band voltage, these are the important ones. Fine. So let's move forward. That was the review of last class. Now let's move forward. In today's class we will be concentrating let's start from the last topic what we have already studied. As we have already studied the oxide structure, the metal oxide structure. Now what we'll do, we will try to calculate the potential difference between the silicon and the metal. Fine. The potential difference between silicon and the metal, and that is very important. So let's see how to calculate it. So let's start. What we'll be doing here, we'll be calculating the potential difference or the work function difference between the Fermi potential, between the work function of the silicon and the work function of the metal. So let's calculate it. Just a second. So let's start. Actually what we have already done, we have understood that the band is bending. Fine. And the band is bending due to the inbuilt potential difference. Now we wanted to calculate that particular potential difference. What is that potential difference between the metal and the semiconductor? Fine. This we need to understand. Fine. Now let us start calculating it. Before calculating it, I would like to let you know that this calculation is also given in the book that is CMOS VLSI design by Sung Mo Kang. Fine. And this particular analysis is example 3.1. This particular analysis is example 3.1 of that book. Fine. In this example, let's see what has been done. Here what we are trying to do, we are trying to calculate the built-in potential of a MOS structure. Fine. So for that, what we need to do, we need to calculate the work function of semiconductor and subtract that work function. Did you remember the work function? Work function is phi s. Fine. And what is that? That is the amount of energy required to move this charge carrier out of the silicon into the free space. Fine. Please remember this. So we need to find the difference between work function of silicon and the work function of metal gate. This is how we'll go on. Fine. Work function of this metal gate and work function of the silicon. So what will happen then? What is that? This is the difference of potential. This is the difference of potential between aluminum, this metal, and the semiconductor. Now from that analysis we'll get to know that what is the built-in potential of the MOS structure. Fine. This is very important because this is your MOS structure. This is your MOS structure, and in the MOS structure you have when you have combined all these material, then there is a built-in potential between this terminal and this terminal. So we need to calculate that built-in potential, and let's analyze what is that built-in potential mathematically. Fine. That has created the band bending. Fine. So let's start that. What you need to do, you need to calculate the built-in potential, that is work function of the metal gate minus the work function of silicon. Fine. We are starting from from the gate towards the silicon. So the built-in potential is work function difference between the metal and the silicon. Now the work function of metal is standard and it is already given here. If you can see, the work function of metal is already given here. It is 4.1 electron volt. Now let us calculate the work function of silicon. Work function of silicon, what is the work function of silicon? The amount of energy required to move this charge carrier out. Fine, this is the work function. Now how to calculate this? Let's see. To calculate this, we have already given the band gap of a silicon. We all know the band gap of silicon. Band gap is difference between EC and EV, that is 1.1 electron volt. So with this we can calculate the intrinsic potential. Fine, that is half of EC minus EV when you do EC minus EV by 2. So what will happen? That is 1.1 divided by 2, and that comes out to be 0.55. Fine, so this is the intrinsic formula. This is the intrinsic formula, 0.55 volt. Fine. Now what we have obtained? We have obtained this much. We have obtained this much energy level. Fine. Now we wanted to find this entire thing, this entire energy from here to here. Now for that we already have this electron affinity for silicon, that is 4.15 electron volt, that is also standard. Now it has been given that this is what? This is Fermi potential. Let me use a different pen. This is what? This is a Fermi potential. Fine. So Fermi potential is also given to us, and that is also standard. It is given as 0.2 electron volt. It is given as 0.2 electron volt. So Fermi potential is also given to you, that is 0.2 electron volt. Now the work function of silicon, let's concentrate on work function of silicon. Work function of silicon is this much. Just a second. Yeah, work function of silicon. The work function of silicon is this much. This much is the work function of silicon. You already know this. You already know this, and you have calculated this. Just now you have calculated it as 0.55 electron volt. Fine. So when you add all these three things, you will be able to get this entire thing. You will be able to get this entire thing, and this is what? The work function of silicon. So let us add all these things to get the work function of silicon. So the work function of silicon can be calculated as, it can be calculated as 4.15, that is the electron affinity plus the intrinsic level, intrinsic Fermi level, that is EI. This is EI, and the Fermi potential, that is 0.2 electron volt. Fine, and all these things comes out to be 4.75. yeah, all these things comes out to be 257,719. no, it comes out to be 4.9 electron volt. Fine, so it comes out to be 4.9 electron volt. This is what the work function of silicon. So we have calculated the work function of silicon, and it is how much? 4.9 electron volt. Please remember what is work function of silicon. This is the amount of energy required to get the charge carrier out of the silicon from the Fermi level. Remember, from the Fermi level. Fine. Now the work function of metal. It is also already given to you. Now you can find the difference between the work function of semiconductor, that is silicon, and the metal. So that is phi m minus phi s, phi m minus phi s. So this was 4.1 minus 4.9, 4.1 minus 4.9, and it comes out to be minus 0.8 electron volt. So what is this? This is the built-in potential between the aluminum gate, between the gate and the MOS structure and the silicon. Fine. So this is the built-in potential. How much? Minus 0.8 electron volt. Fine. So this is the potential. This is the potential which was responsible for band bending. In the last class, which we have seen that this was the Fermi potential. This was the Fermi potential of metal gate, and this was the Fermi potential of silicon. Fine. Now the bands were bending something like this. This was the intrinsic band. This was the your conduction band, and this was your valence band, and this is how it was bending. Look at this, the bending is downwards. What was the reason? The reason was this minus 0.8 electron volt, and because of this minus 0.8 electron volt, all the bands were bending downwards. Fine. Now one thing can be done here. If you apply a voltage across these terminals, please listen it carefully. If you apply a voltage across these terminals, fine, and what kind of voltage? A DC voltage, I'm sorry, DC voltage of what polarity? A polarity opposite to this. That means positive 0.8 electron volt, positive 0.8 electron volt. Then what will happen? Because of positive 0.8 electron volt, the band, the inbuilt potential in this MOS structure, the inbuilt potential in this MOS structure will go away. Similar to the PN junction, which we have already studied. In the PN junction also there was a built-in potential, that is known as threshold voltage or built-in potential. So when we apply the forward bias voltage, then the built-in potential or the depletion layer, that goes away. Fine. Similarly, in the MOS structure also, if you apply a positive this much voltage, then the bands which were bending, something like this, they will become flat. Fine. They will become flat. And as I have already told you in the last class, that the voltage which is responsible for making these bands flat will be known as flat band potential or flat band voltage, denoted as phi FB. So from this analysis we got to know that the flat band voltage, the standard flat band voltage for silicon is 0.8 electron volt. It is 0.8 electron volt. Fine. And let's move forward. Now we will concentrate on the MOS system under external bias. Fine. So what we'll do, we will understand the entire MOS system when we apply a external voltage on the gate terminal. Fine. So hello students, let us now focus towards the MOS system under external bias. Fine. So now we'll study that same MOS system under external bias. So what kind of bias is that? That would be the voltage which is applied onto the gate terminal. Fine. So now we are studying the MOS system under external bias. Fine. Now depending upon the type of voltage which we are applying on the gate terminal, there can be three different types of operations. Fine. The first one will be known as the accumulation. First one will be known as accumulation. The second one will be known as depletion. The third one will be known as inversion. This is what the different types of operation of a MOS system, not MOS transistor. I'm talking about the MOS system. These are the three different types of MOS operation when you apply different types of gate voltage onto the MOS system. Fine. So let us consider the first kind of arrangement, that is accumulation mode. Fine. So what happens in accumulation mode? You take the same MOS which you have already taken. I'll take the same MOS, this rectangular p-type terminal, then a silicon oxide, then a metal gate and a gate terminal attached to it and a substrate terminal attached to it. Fine. So what I am doing, I am applying a gate voltage here, VG, and I am applying a substrate voltage here which I have already kept at equal to 0. That means somehow I have grounded it. Fine. Now let us focus towards the amount of gate voltage which we are applying here. Fine. So let us take the first condition when we are applying a negative voltage. When we are applying a voltage less than 0 volt, then what will happen? Actually we all know that this complete system, which is consisting of the metal, that is aluminum metal, silicon oxide and silicon substrate, this is already in the equilibrium condition. Fine. So in the equilibrium condition, the number of charge carriers which are present in this substrate, they are already p-type, because it's a p-type substrate. Fine. So definitely their majority charge carriers are holes. Fine. And minority charge carriers are electrons. Now what happens when you apply a negative voltage? When you apply a negative voltage, then that negative voltage will try to attract all the holes towards the surface, with all the majority charge carriers which are holes towards the surface. Fine. And all the holes accumulate at the surface. These holes accumulate at the surface. That's why this mode is known as accumulation mode. This is the reason why it is known as accumulation mode, because all the holes, they appear at the surface. That's why it is known as accumulation mode. Now let us look at the band diagram, because we are focusing on the band diagram since the beginning of the lecture. So let us focus on the band diagram, how the band diagram is affected. So you remember, we always draw the band diagram something like this. This is the silicon oxide. Fine. This is the silicon oxide. Then we have the aluminum here, and then we have the bulk silicon substrate. We call it as silicon substrate. Fine. So silicon substrate here. Now what was the band diagram when it was in the equilibrium condition, initial condition? Let's see it. In the initial condition, the Fermi level was aligned. In the initial condition, the Fermi levels were aligned. We all know that. So the Fermi level of aluminum was something like this, and the Fermi level of the silicon was also aligned to this. So we called it as phi m. The Fermi level, I'm sorry, not phi. Phi means potential. So we represent it as E Fm. E Fm. That means the Fermi level of metal gate, and then we represented this as the Fermi level of p-type silicon, EFP. Fine. So that means it is a Fermi level of p-type substrate. And what happened to the other energy bands? They got banded downwards due to the potential which is appearing across these terminals. We have already calculated that potential, and that was a negative potential. Because of that negative potential, these bands will were like this. These bands were straight in the bulk, but at the surface they were banded. Fine. So let us make with a different color so that it would be distinguishable. Fine. And then you have two more bands. Those are, one is your intrinsic band. So let us make the intrinsic band as dotted, because intrinsic band is a hypothetical backend, because it is not here, it has already vanished once you have doped it. Please think about this. Fine. So I have made it as dotted. And then the conduction band is here. It is also inverted, also banded. And then the valence band, it is also banded. So this was the structure when it was in thermal equilibrium. That means equilibrium means no external voltage was applied. Now what happened? Now we have already applied a voltage like this, a negative voltage. So what happened due to negative voltage? Due to negative voltage, let us first consider about the aluminum gate. What has happened to aluminum gate? You are applying a negative voltage here. Fine. Negative voltage means you might have applied a battery something like this. Is it okay? So you are applying a negative voltage something like this, and how it is applied? You are actually providing more number of electrons. Negative terminal of the battery provides electrons, so you are actually providing more number of electrons to the metal. Is it okay? You are providing more number of electrons from the negative terminal of the battery to the metal. So what should happen to the Fermi level of the metal? Where are more number of electrons find? More number of electrons are always find towards the conduction band, while more number of holes are found towards the valence band. So what would happen to the Fermi level of the metal? It should go towards the conduction band. Fine. So we will draw this again. So this was the original Fermi level of the metal, and now the new Fermi level of the metal goes towards the conduction band. It goes towards the conduction band. And how much level does it goes up? It goes up towards the total amount of potential is Vg, the gate voltage which you are applying here. Fine. And since we are measuring it in electron volt, so I write QVG here. Q means the charge on an electron. Fine. So this is electron volt. This much amount of space the Fermi level of aluminium goes up. Fine. Now let us talk about the silicon. What happens inside the silicon? Inside the silicon, more number of holes appeared here. If you look closely, more number of holes appeared here. Now what will happen? What should happen? See, in the bulk means this p-type substrate. So in the bulk nothing happens. So all this thing in the bulk, they will remain same, they won't change. Fine. What will happen? Only the changes will occur at the surface. Fine. So let's see what should happen. More number of holes are here at the surface. If you see, more number of holes are at the surface. So what should happen at the surface? The Fermi level should go towards the fine. So the Fermi level should go towards the valence band. Now let's draw this again. Erase only this much part. Let us erase only this much part, because in the bulk the band diagram will be same. The only change will be at the surface. So what should happen now? The Fermi level should go towards the valence band. Since we have already drawn Fermi level like this, So to reach this Fermi level towards the valence band, what should happen? The valence band should be drawn something like this, so that it should be closer to the Fermi level. So I draw it like this. What does it mean? It means that the Fermi level has moved towards the valence band. Why? Because there are more number of holes here, and more number of holes represent that your Fermi level is towards the valence band. If you remember, in the p-type semiconductor, what happens in a p-type semiconductor? In a p-type semiconductor, the Fermi level, there are more number of holes, therefore the Fermi level moved towards the valence band. And same thing happened here. Same thing happened here. The Fermi level goes more towards the valence band at the surface, because the changes are happening only at the surface. Fine. And same happens with the intrinsic band. Your intrinsic band also banded like this, and same thing happens with the conduction band. Fine. So your Fermi level becomes more closer to the valence band as compared to the conduction band and the intrinsic band. Now I advise all you students to please look this very closely. Please don't get confused that sometimes we are moving Fermi level, sometimes we are moving conduction band and valence band. See, this is just the representation. This is not the actual thing which is happening inside the material. This is just the representation of energy levels. What I wanted to do, I wanted to make this Fermi level closer to the valence band. So what I did, I made valence band closer to the Fermi level. That means the same, that the Fermi level has gone towards the valence band. And since the Fermi level goes towards the valence band, that automatically means that it will go far from the intrinsic band as well as the conduction band. So what I did, I made this intrinsic band and the conduction band banded towards up. So this is how it will look, and this is known as accumulation mode. Why? Because the holes got accumulated at the surface, and when it happens at a negative gate voltage, when you apply a gate voltage less than 0. Fine. Now let us come towards the next condition. The next set of condition is when you apply a little positive voltage. Please remember, only little positive voltage. I am not talking about the gate voltage which is lower than the threshold voltage or higher than the threshold voltage. I am just saying that let us apply a little gate voltage. Fine. Now take the second condition. Take the second condition when we applying a little gate voltage, a gate voltage higher than 0. Fine. Little gate voltage. Now what will happen? Let us draw the silicon substrate again. Let us do the silicon substrate again, our silicon oxide. You people also draw these things again and again, so that it would be habitual for you. Once you keep on drawing these things, then you people will become habitual towards this. Fine. So we have made the substrate voltage equal to 0. So what we are doing, we are keeping the substrate voltage constant equal to 0, and we are varying the gate voltage. Now what we have done, we have applied a little gate voltage which is greater than 0. Fine. For a p-type substrate, remember. Now what will happen? Please analyze what will happen. See, this substrate contains more number of holes and less number of electrons. Fine. Now what will happen with the positive gate voltage? With the positive gate voltage, a positive electric field is applied here. Fine. With a positive gate voltage, a positive electric field is applied like this, in this direction. What type of field? Positive field. What will this positive field do? This positive field will repel all the holes downwards. Fine. Now what will happen when they are repelled downwards? What remains at the surface? Please think for a while. Pause this video and think for a while that what will happen when you repel all the holes. What remains behind? There remains a depletion layer. What will be remained? There remained a depletion layer. Depletion layer means a layer which consists of no charge carriers, almost no charge carriers. Fine. So a depletion layer is formed, this much amount of depletion layer is formed at the surface. Depletion layer means the area which is deprived of any charge carrier. There is no charge carrier, neither holes nor electrons also. Fine. Although if we apply a higher gate voltage, that's what I am saying, that this is a small gate voltage. If I apply a higher gate voltage, these electrons would be attracted towards upside, but I am not talking about that condition. That condition will come later on. Now what I am taking a different condition where we are applying a low gate voltage, a low positive gate voltage, and because of that low positive gate voltage, the holes were repelled and the surface becomes depleted with charge. Depleted with charge means there is no charge carrier, and because there is no charge carrier, what happens at the surface? A depletion layer is formed. Fine. Let us take the size of that depletion layer as xd. xd, let me make it again, it is xd. Fine. Let us take the length of this. What I am taking length of the depletion layer. The depletion layer is of some size. Fine. So I am taking the length of that particular depletion layer as xd. Fine. Now let us understand what happens with the band diagram. That is also important thing. So what happens with the band diagram? Again we will draw the same kind of band diagram. First we will draw the silicon oxide. This is SiO2, this is SiO2. Fine. So this is silicon oxide. Fine. Just a second. This is silicon oxide, this is aluminium, and this is bulk silicon. Fine. Now let us draw the original condition. We always have to draw the original condition and then we will draw the changes. So our original condition was something like this. This was the energy of the Fermi level of the metal gate, and it was aligned with the energy of the Fermi level of the silicon, when F and P type. Fine. Now what was the level of intrinsic band? It was something like this. Conduction band was something like this, and valence band was something like this. Fine. This was the condition. Now what you have done, you have applied a positive voltage. Fine. So let us consider what happens with the aluminium. What you are doing, you are applying a positive voltage, so you are applying more number of holes here. Fine. More number of holes means what should happen to the Fermi level of gate or the Fermi level of metal gate? What should happen to it? Since you are applying a positive voltage, that means you are applying holes to it. So holes means, where are holes available? Holes are available in the valence band. Please remember this, holes are available in the valence band. So Fermi level will now move towards the valence band. So how should I make it? I will make it like this. The hole will move towards the valence band. So I will make it like this. Just a second. I will make it like this. Make this condition like this. The holes should move towards the valence band. Fine. So I will make this condition like this. I'll make it dotted. Yeah. So this was the previous one, and this is the new one. Where is the valence band? Valence band is towards downwards. So this is the new one. So it moved downwards. And how much, by how much potential it moved? It moved towards the it moves with the voltage Vg, because we are applying Vg, and since we are measuring in the electron volt, so I write it as QVg. So it has moved by a value of QVg downwards towards the valence band. And now what happened at the surface of the silicon? That is important to analyze, because only the changes only occurs at the surface of the silicon, not in the bulk. So what happens at the surface of the silicon? At the surface of the silicon, it is deprived of any charge. There is no charge. So what should happen if there is no charge? Initially it was something like this. The intrinsic band, the valence band, they were all banded downwards. Fine, they were all banded downwards. Now there are no holes here in this particular region. Fine, and the majority holes were repelled. Fine, the majority holes were repelled. Now what will happen in that case? Since the majority charge carriers were repelled, the majority charge carriers are repelled. Now it will look like a intrinsic semiconductor because the majority charge carriers are repelled. Fine, so the condition becomes similar to a intrinsic semiconductor. So what should happen? Actually the Fermi level now becomes aligned with the intrinsic level. This was the intrinsic level. Fermi level become aligned to the intrinsic level. Why? Because these holes were repelled. What are holes? Holes were majority charge carriers. So now what will happen? The density of holes in this area becomes, although this is depleted with any charge carrier. So since this is depleted with any charge carrier, that is original silicon, because original silicon does not have any free charge carrier. Please remember, the original silicon that has the Fermi level of original silicon is intrinsic Fermi level. You call it as EI. Fine. So what happens in original silicon? In the original silicon there is no free charge carrier because it is not doped. So it is neither having holes, neither having electrons. Fine. So the same condition appeared here. It is depleted of any charge, so there is no charge carrier here. And since there is no charge carrier here, so it behaves similar to a intrinsic semiconductor. And in that case, the intrinsic level should come closer to the Fermi level of the silicon. This is the Fermi level of the silicon, and it came closer to the intrinsic. And since the intrinsic bent downwards, therefore the conduction band, this was the conduction band. Conduction band also goes downwards, and the valence band also goes downwards. This is the condition of this is the condition of depletion. Fine. The second condition, this is known as depletion condition. When you apply a little positive bias. Fine. This is known as depletion. Now we proceed towards the third condition. Fine, we proceed towards third condition. Before proceeding towards third condition, this is the size of the depletion layer, and please remember this size will always remain same. Even if you apply a very high positive voltage, this depletion layer size will always remain same, and this will be very helpful. We will mathematically derive the size of this XD. First we go to the third condition, then we will come back to the second condition, and we will derive the XD. This derivation of XD will be helpful in deriving the threshold voltage of entire MOS transistor. Fine. So let us first move towards the third condition, and then we'll come back to the second condition. Let's go towards the third condition. The third condition is when you apply a positive voltage, higher positive voltage. Fine. So let's go towards that condition. Just a second, we'll go towards that. So in the third condition, what we'll do, we'll study the third condition would be the inversion condition, and that is one of the most important condition which will make you understand how the entire MOSFET works. Fine. So in the inversion condition, we'll be having a gate voltage, a higher gate voltage, higher than 0 volt. Fine. A high positive voltage. So what happens when you apply a higher positive voltage? Let us consider the again the MOSFET structure. We will draw the MOSFET structure. So you have p-type silicon, then you have silicon oxide, then you have aluminum gate, then you have gate terminal, then you have the substrate terminal, and you are applying this 0 volt at the substrate terminal. You are applying a very high gate voltage. Now what will happen? Let us consider this. Let us draw the previous condition. What happened in the previous condition? Due to applying a positive voltage means the electric field is something like this. It is going downwards. The electric field is going downwards, and because of the electric field which is going downwards, the holes would be repelled. This is what we have studied in the last condition. And what has happened? A depletion layer has been formed here. This is what we have studied in the last condition. Fine. Now as we are applying a very high positive potential, now what will happen? What this layer is, please tell me. This layer is a depletion layer. Fine. And what does depletion layer means? Depletion layer means it is deprived. Deprived, you know, deprived of any charge carrier. Deprived means that has no charge carrier. That has no charge carrier. Fine. So it is deprived of any charge carrier. Now what is left behind? Please tell me, what is left behind? The ions are left behind. Why there are ions? Because this is a p-type semiconductor, and what is present in a p-type semiconductor? It's p-type semiconductor. And what is present in a p-type semiconductor? In a p-type semiconductor there are majority charge carriers, and the majority charge carriers are obtained because of what? Because of the atoms of what type of impurity? Atoms of acceptor type impurity. So because of atoms of acceptor type impurity, the p-type substrates have been obtained. You all know this. Now what I'm trying to say, what is inside this depletion layer? Inside this depletion layer there are Na ions. Fine. There are Na ions. Fine. So these Na ions are Na negative ions. If you have studied in your electronic courses, these are Na negative ions. Why they are negative ions? Because they have accepted the extra electron of the silicon, and holes have been created here. Majority charge carriers are holes. So all the holes were moved downwards due to this positive voltage, high positive voltage. And what is left behind? The depletion layer. And what is inside the depletion layer? The negative ions of acceptor impurity, that is Na negative. Acceptor impurity can be anything, either most of the abundant used is boron. Fine. So this is acceptor type impurity, and this entire depletion layer consists of acceptor type impurity of negative type. Please remember, what type of ion? Negative ion. Now what you are applying? You are applying a positive voltage, and this positive voltage will move the depletion layer downwards. This higher positive voltage, this very high positive voltage, will move the depletion layer downwards. Now what will happen? Now let us draw it again. Now what will happen? You have the same silicon oxide layer, you have same aluminum gate, you are applying a very high positive voltage. Fine. And that positive voltage is something like this. Now due to this positive voltage, this layer gone downwards. What layer? The depletion layer. Fine. And remember, I have told you the length of this, the width of the depth of this depletion layer, we show it as XD, and this will always remain XD irrespective of this voltage. Fine. Because after a particular voltage, instead of this depletion layer increase in this depletion layer will not increase. All this depletion layer will move downwards. Fine. Once this depletion layer move downward, and what is beneath this? Beneath these are majority charge carriers of holes. And what is left behind? Please tell me. Please think for a while and tell me what is left behind. What are the contents of this p-type semiconductor? This p-type semiconductor contains holes which are majority charge carriers. And what happened to the holes? They all came downwards. Then they contains the Na negative ions. What happened to Na negative ions? They also came downwards because of high gate voltage. And what remains behind? Remains behind are minority charge carriers. And what are minority charge carriers in p-type substrate? Those are electrons. You can understand this theory in another way, in a different way. Let's understand this like this, that this is a very high positive voltage. Now a positive voltage will definitely attract a negative charge carrier. And what is a negative charge carrier? That are electrons. Fine. So whatever electrons which are present inside the p-type semiconductor, definitely there are electrons. Those are minority charge carriers. So those all minority charge carriers got accumulated at the surface of the silicon. Those all electrons got accumulated at the surface of the silicon. Fine. And the surface of the silicon will start behaving like a n-type semiconductor. Why? Because n-type semiconductor will have majority of electrons, and all the electrons appeared at the surface. So now your p-type semiconductor at the surface, please remember, only at the surface, will start behaving like a n-type semiconductor. And that is why this condition is known as inversion condition. This condition is known as inversion condition. Inversion condition means the p-type semiconductor has now started behaving like a n-type semiconductor. Fine. And let us see the same thing using a band diagram. Now you will understand that why we are drawing the band diagram again and again. In this condition, when we draw the band diagram, you will be able to understand that why we are trying to draw the band diagram again and again. Fine. So let us draw the band diagram. That is important thing. Let us draw the band diagram. So similarly, in the last two conditions also, we have drawn the band diagram of the original MOS structure first, and then we have seen that what is the effect of external gate voltage. So first we will draw the external band diagram. The band diagram of MOS structure. So this is silicon oxide, this is silicon oxide, this is aluminum gate, this is silicon, bulk silicon. Now the Fermi level of aluminum was aligned with the Fermi level of silicon. We call it as like this. The Fermi level, the Fermi level of metal is aligned with the Fermi level of silicon, p-type silicon, and the bands, the intrinsic band for example was banded downwards, the conduction band was banded downwards. Fine. And similarly the valence band was banded downwards. Now let's see what changes do occur in the Fermi level of metal gate and the Fermi level of p-type silicon. Fine. Then you will understand that why we are drawing the this band diagram again and again of original silicon. Fine. Now we need to analyze the band diagram of in third condition, where we have applied a higher gate voltage. So let's see what would happen. See, we have applied a higher gate voltage here. Now what can happen? What will happen with the metal gate? Let's analyze what will happen with the metal gate. So at the metal gate you have applied a higher voltage. Higher voltage means positive voltage. Positive voltage means more number of holes. So more number of holes, that means where are holes find? Holes are find always in the conduction band, valence band. Please remember, holes are find in the valence band. So your Fermi level of the metal should move towards the valence band, because this is valence band downwards. Fine, it should move towards the valence band. So first what we'll do, we will move the Fermi level towards the valence band. So what we'll do, we will make the original band as the with the dots, with the help of dots, and then we move the band, this formidable band of metal downwards. So now this is your new one, this is your new Fermi level of metal, and it has moved by what distance or what potential? It is moved by the potential which is equal to the gate voltage, because we are measuring in the electron volts, so I multiply it by Q. Fine. Now let us move forward. Now what will happen to the silicon? Now let us focus towards silicon. What will happen to silicon? In the silicon, we have put it with high positive voltage. So what will happen? The electrons comes towards the surface. Fine, I have explained it with the two different theories. One theory is that all the holes are repelled, majority charge carriers are repelled, and the depletion layer also moves downwards. So what remains behind? Remains behind are the minority charge carriers. So what are the minority charge carriers in the silicon? In the p-type silicon, that are electrons. One of the theories is that the positive gate voltage, higher positive gate voltage, will repel the holes while it will attract the electrons, minority charge carriers. So in both the theories, the electrons will appear at the surface of the silicon. Fine. Now look at this. What will happen? What we can understand with this diagram is that electrons are accumulated at the surface. Fine. So when the electrons are accumulated at the surface, so this is still the silicon, material is not changed, material is still the silicon. So we can say that this silicon becomes n-type. Why? Because there are majority charge carriers, the majority charge carriers in this region of silicon, only in this region. Let us focus this region, only in this region of the silicon, this much region. Just a second. Yeah, this much region, only in this much region of silicon is electron. So I'm talking about this much region. So in this much region, the majority charge carriers are what? Electrons, because all the holes were repelled. Now this starts behaving like a n-type semiconductor rather than p-type semiconductor. That's why this condition is known as inversion. This condition is known as inversion. Fine. This condition is known as inversion. Fine. So instead of acting like a p-type semiconductor, it starts acting like an n-type semiconductor, because it has majority charge carriers. Now it has holes on the surface, electrons on the surface. And in the later stage, when we will study MOSFET, complete MOSFET transistor, we will see that this layer of electrons will be helpful for the conduction of current between drain and source. Fine. So let us see towards the band diagram of inside the silicon substrate. What will happen inside the silicon substrate? So let me erase this part, because only the changes occurs only at the surface. I am telling you again and again, the changes will occur only at the surface. Fine. So rest of the bands are same. Now what will happen at the surface? Please tell me. The Fermi level of p-type, let us first draw the Fermi level of p-type. So Fermi level of p-type would be same. Fine. Now what would happen? The Fermi level is already aligned with the Fermi level of metal gate, so I'm not bending it, but the bending will happen in the conduction band, intrinsic band and the valence band. Why? Let me tell you. This silicon at the surface, only at the surface. So let me highlight this portion, only at the surface. So the silicon only at the surface is acting like n-type. Please remember, this much portion is still p-type. It's a p-type semiconductor. That's why it's a p-type semiconductor. That's why I have drawn it like this. It's a p-type semiconductor. It's still p-type semiconductor. Just a second. It is still p-type semiconductor. So what I have done, I have put the Fermi level closer to the valence band. I have put the Fermi level closer to the valence band. That shows that this is a p-type semiconductor. Now what happens at the surface? At the surface, the Fermi level goes closer to the conduction band. Why? Just because of the fact that at the surface the semiconductor is behaving like n-type semiconductor. Now what will happen? This Fermi level will go closer towards the intrinsic conduction band. So since it is going towards the closer to the conduction band, so it will also go closer to the intrinsic band. I am repeating, since it is going closer to the valence band, conduction band. What? The Fermi level is going closer to the conduction band, so it is also going closer to the intrinsic band, and it is going away from the valence band. So with the bending, how we can draw it? Our Fermi level is this, it is going away from the valence band, so we can draw the valence band like this. It is coming closer to the conduction band and since there are majority electrons, so it has almost come very close to the conduction band, and it is also coming closer to the intrinsic band, and in fact it has crossed the conduction band, intrinsic band, I'm sorry, it has crossed the conduction band. Why I have drawn the band diagram like this? I will explain the same thing with this diagram. How do you draw the band diagram of n-type semiconductor? What you do, you make a conduction band, you make a valence band, you make a intrinsic band, intrinsic level, and for a n-type, what you do, you make the Fermi level closer to the conduction band, between the intrinsic band and the conduction band, somewhere here. This is the Fermi level of n-type semiconductor. The same thing I have drawn at the surface of the silicon substrate. Same thing. If you can see that the Fermi level is between the conduction band and the intrinsic band, and here also the Fermi level, see the Fermi level is, I'm drawing with a different pen, let's see, yeah, the Fermi level is where? Is closer to the conduction band, between the conduction band and the intrinsic band, if you can see, and it is away from the valence band. So this particular region is behaving like n-type, and the silicon bulk is behaving like p-type. That's why this condition is known as inversion condition. And one more thing which you need to understand here, that why this condition is occurring. This condition is occurring when you apply a surface when the surface potential, the potential in this region, when the potential in this region becomes equal to the Fermi potential of this region. Please remember, I am again repeating, when this condition appears, when this inversion condition appears, this inversion condition appears when the surface potential, which we represent as phi s, becomes equal to the Fermi potential of what? Of bulk silicon. So this is the condition when the inversion occurs. Fine, this is the condition when the inversion occurs. So this is the condition of inversion, and in the later stage when you will study MOSFET, you will able to understand that this is the reason why the NMOS and PMOS are able to conduct current between drain and source. Fine. So this was an important condition, the third condition of inversion. So we have studied the three conditions of operation of a MOS structure, that is accumulation, depletion and inversion. Fine. Now let us come back to the second condition, because in the second condition we have an important derivation. Let's come to the second condition. In the second condition, this was the third condition, this is the second condition. In the second condition we have studied that a depletion layer forms what is second condition? If you remember, the second condition was when you are applying a little gate voltage, a smaller gate voltage. So what will happen? The depletion layer is formed at the surface. Fine. So this depletion layer, now what we wanted to study here, we need to study the size of this depletion layer. We measure this size, as I have already told this, we measure this size as XD. The size is XD. So we need to calculate the size, and we also need to calculate the total charge inside this depletion layer. Does it have any charge? Please tell me, does it have any charge? Yeah, it has charge. What type of charge? Na negative ions. Please remember, it is depleted with charge carriers. It does not have any moving charge carriers, neither electrons nor holes. Please understand this carefully. This particular area is depleted. Depleted means it does not have holes, it does not have electrons, but it has some charge. What type of charge? Ions. Those are known as immovable ions. Why we call it as immovable? Immovable. What is immovable? Immovable means which is not able to move. So immovable ions. What type of ions? Na negative ions. So it has Na negative ions. Fine. Since it has Na negative ions, so because of Na negative ions, negative means some charge. Fine. Although it is not moving, but it is negative. It is what type? Negative. So that means it has some charge. So we will calculate the charge, and we will also calculate the size of this depletion layer. Both are important when we will calculate the threshold voltage of entire MOSFET. Fine. So we will come again back to the second condition, where we will measure this charge, this size of this depletion layer. Fine. So let us start this one. Let me again draw the second condition. The second condition is something like this. In the second condition, this is the silicon substrate, this is the silicon oxide, just a second, yeah, this is the silicon oxide and this is the silicon, and we have applied a positive gate voltage and little positive gate voltage. What will happen? The depletion layer has appeared at the silicon surface. Fine. So the depletion layer has appeared at the silicon surface. Now we need to calculate the depth of the depletion layer. Fine. And we need to calculate the total charge in this depletion layer. Fine. We need to calculate two things. So let us start. Let us start. Now what we'll do, we will start with the total charge in this small but finite size of depletion layer. Fine. So we will start with a charge in this finite layer. So let us say the charge in this finite layer is dq. Fine. And that is equal to q, just a second, that is equal to q multiplied by Na multiplied by dx. How did I write this? See, what is the total amount of charge present inside this depletion layer? As I've already told you, what are the charges inside this depletion layer? Only Na negative ions. There's nothing apart from Na negative ions. Since there is just Na negative ions, so what I've taken Na. How much charge does it have? Please tell me, how much charge does on each Na negative ion has? This Na negative ion is because of what? One extra electron. This acceptor impurity has taken one extra electron from silicon, so it has taken one electron, so it has a charge of single electron. That's why I have multiplied Q here. Fine. And this QNA means the charge of all the acceptor ions, and when I multiply it with the dx, that means this is the charge of only the acceptor ions in the this much depletion layer. Fine. I'm again repeating why I have written the total charge in this depletion layer as QNA dx, since the only charge I'm not saying charge carrier. Please don't confuse between charge carriers and charge. Fine. These are immovable charges or ions. So the total charge inside this depletion layer is equal to QNA dx. Na means the acceptor ions. So the only charge present in this depletion layer is acceptor ions. So I have taken concentration of acceptor ion Na. Now, what type of charge is on every acceptor ion? That is equal to the charge of one electron. That's why I have taken the Q. I have multiplied Q here. So what does this quantity represent? This quantity represents the total charge due to acceptor ions. Total charge due to acceptor ions. Fine. Now, when I multiply this quantity with dx, then what will happen? That means the total charge due to Na ions in this much amount of depletion layer with the size is dx. This is what it means. Fine. So I'm starting with this quantity, which is QNA dx. QNA dx. One more thing, a negative sign will appear here. Why negative sign? Because these are Na negative ions. That's why a negative will appear here. Fine. Now we will make use of one important equation which you might have studied in electronics. I'm sorry, not electronics. You might have studied in mathematics 2, M2, mathematics 2 of your BTech syllabus. That is Poisson equation. Fine. So I'm repeating it here for you people. I will make use of a Poisson equation. What does this Poisson equation say? This Poisson equation says that it relates the potential in a particular region. So I am talking about this region, this particular region. It will relate the potential. I write it as phi s because it is surface potential, so I write it as phi s. So it relates the surface potential with the total charge in that surface. Fine. So what is that Poisson equation? That is phi s surface potential, total surface potential in a small area, that is d phi s. D phi s equals to the size of that depletion layer or the length of the depletion layer multiplied by the charge in the depletion layer, that is dq, divided by the permittivity of that particular area. So what is the permittivity of that area? That area is nothing but silicon, so I will take epsilon Si, that is the permittivity of silicon. So this is the Poisson equation. What does it say? I am again repeating. It says that the potential of that area what is that potential? That is phi s. Phi s means I've taken s. S means surface potential, because this depletion layer is at the surface of the silicon, surface of the MOS structure. That's why I've taken as phi s. That is equal to minus the size, the length of that depletion layer, multiplied by the charge of that depletion layer divided by the permittivity of that depletion layer. Fine. Now using this, what will I do? I will put the value of dq from this equation. Fine. So from this equation I will put the value of dq here, and let's see what will come. It comes out to be since it is still this is having negative, and this Poisson equation is also having negative, so they become positive, and the total expression is something like this: q na x divided by epsilon si dot dx. Fine. Q na x upon epsilon si dot dx. This is what d phi s. So now your charge, the surface charge, or your surface potential is equal to q na x dot dx divided by epsilon si. Fine. So let us try to calculate it. So what we'll do, we will integrate this particular expression. So we will integrate this particular expression. Let's do it. We will integrate that particular expression. So again let me again write that expression. The expression is d phi s equals to q na x divided by epsilon si dot dx. Fine. So what I'll do, I'll integrate it. D phi s equal to q na x upon epsilon si into dx. So let us decide the limits of the integration. For the d phi s, the limits of integration would be, for that we need to go to the, so let us now decide the limits of integration. Fine. So for the limits of integration, let's go to the figure again, and the portion which is under consideration is this much. This is the portion which we are considering. It's a lot of mesh there. Let me clean it first. We are considering only this much portion. Fine. And there is a depletion layer. Now this depletion layer consists of negative ions. We all know that. Fine. Negative ions. Now we want the limit of integration. Limit of integration as the limit of surface potential, the limit of potential. Fine. Potential from this place to this place. Fine. Starting from this place to this place. So what is potential at this place? Potential at this place is nothing but the Fermi potential of the silicon, and that is phi fs. That is Fermi potential of the silicon. And potential at this place is nothing but the surface potential. We have already named it as surface potential. So the limit of integration would be phi fs to phi s, where phi fs denotes the Fermi potential of the silicon and phi s denotes the surface potential. Fine. So let's put that limit. We'll put the limit as phi fs, or phi f simply we say as phi f, to phi s. Phi f to phi s. Just a second. Phi s to phi f to phi s. Now let us find the limits for the second integration. The second integration belongs to the dx. Dx means the size of the depletion layer. So the size of the depletion layer is from 0 to